morning, class. Welcome to CCS 440 Senior Design Review. My name is Julie Kim. Today I'm going to present the design of a processor. Today's agenda is going to be brief introduction and baseline MIP architecture brief overview, and MIP architecture implementation, hardware enhancement instruction and verification, and future enhancement hardware architecture, and some current result. The name of the processor is regular processor, which is a MIP 32-bit compatible processor, and the reason I chose this regular as the name of the processor, because there are 4 design principles. The first design principle is simplicity favor regularity, and the design the purpose of the design is to have the small and fast processor. That's why I chose the name as a regular. Just an overview of the architecture is it consists of the memory structure is a big endian format, a byte-adjustable, and it's just signed and unsigned integer. And beside the 32-bit 32-bit register and the register for the program counter, there is another flag register. It consists of only 5 bits. And there are 3 addressing modes, which is immediate, register direct, and register indirect. There are 3 types of the instruction sets, which is the R type, I type, and J type. And the instruction set type is very structural. It has 6-bit opcode, 5-bit, 5-bit, and another. The last 5-bit is the code for the function code. And the general design of the processor is the CPU, and it interfaces with the outside memory module and the I/O module. In the CPU, I have the control unit, instruction unit, and the data path module. The processor is controlled by the state machine, and each clock cycle it generates the control. So the data can flow from the fetch instruction from the IR unit to the integer data path, and it interfaces with the data memory and the I/O memory. And how the I/O memory interface with the CPU is based on the interrupt, which is generated by the I/O memory, and send it to the control unit, which is the state machine, and it send back the interrupt acknowledge when it starts executing the code at the interrupt service routine. This is the general state machine diagram. It has it starts with fetch, decode, and write back the data to the register. And for example, for the R-type instruction, it takes 4 clock cycles to finish the instruction. This is the interrupt service routine, and it starts with the when interrupt happens, it starts with the decrement of the stack pointer by 4, and it saves the program counter or the return address into register 31, and the next step it would save the flag into the stack pointer, which is the address of 3F8, and it go through the same routine. Is decrement the stack pointer and save the return address to the address 3F4, and at the end the stack pointer will point it to the address of 3F4. And this is the instruction unit. Basically, there is a mark at the top right here, which is the selection between the return, the address to execute the next instruction, either the next current address or the jump. That is the branch address, or the 0 selection, which is the jump address. This is the general integer data path. Um, all the circle, they are the control unit for each path. For the data, for the register file, there is a mark right there at the top, which is the selection of 3-bit. Actually, I have the written data back. It has register 8, register 29, register 30 is my selection of writing the data back to the register file. Actually, the register 8, I'll explain a little later why I have the register 8 right there. And for the ALU unit right here, there is a function select control and also the shift amount. And we look into this is the ALU is the wrapper that consists of 4 modules. The barrel shift, multiply, divide, and the MIP module, which consists of all the arithmetic operation. In the barrel shift, I have the shift left, shift right, and arithmetic shift. And the shift amount is only 1 to 31. And actually, I forgot one of the, actually this is the shift amount input. And the output is going to go out of the Y low port. When the data come down out of the ALU port, and it has to go, if it needs to read from the memory or I/O memory, there is a control signal at the I/O or the data memory. Actually, I have only the I/O chip select, read and write. It also applies to the data memory, but I just did not conclude in that.
Can you hold it right there for a second? So the big mux at the bottom has 6 inputs, am I right?
Yes. Right,
So
yes.
what's the last input on the right?
The last input?
Yeah, what's that coming from?
This is the input from, actually, I guess this no, actually it's wrong. This one is connected to the, I think one is from the PC and the fifth one is from the D flag right here.
What's D flag?
D flag is the input from flag data from the flag register. When I write it back to the memory, when to try to
Okay,
push the
and that's
flag
coming
in.
from the control unit then, right?
Yes.
Okay, that helps, thanks.
And this is the verification of the shift left logical, and the function code is 0 and the opcode is 0. If the 4 shift amount to the left, the most significant bit is shifted to the left 4, and it fills the right, the least significant bit of the 0. If it's a 20 bit shift to the left, then it fills the least significant bit of the 20 bit. And this is the right shift logical. The same principle apply when shift it to the right. Then the most significant bit is filled with 0, tested with 20, and the last one, the left most significant bit is filled with 20, 0 bit.
What happens if the shift amount is 0?
Actually, I don't have that. I just start with 1, 2, 3, 4, 5, 3.
But what would happen if it was 0? Because it's possible that the instruction would pass you a 0.
For example, that I didn't actually test it. Probably it just go to 1. I just assume.
Is that your default?
Actually, I did not. When I write this code, I didn't really check it.
You don't have a default? Don't know what your default is? I'm assuming you used a case statement.
Yes, I did.
So what's the default on the case statement?
I don't think I write a default in here.
Oh, we always have a default.
Probably.
Yeah.
I was watching it. So the shift right, it just have it's a little different. The sign bit is always kept. So when you shift right 20 bit, the sign bit there will be 20, 21 as the most significant bit. When we shift right, shift amount is 20. For the enhancement, I have input, output, and return from interrupt. Actually, for input and output, it's just the same as the load and store instruction. It's just that instead of retrieve the data from the memory module, it is for this instruction it retrieve data from the I/O module. And this is the state diagram for the input instruction. It takes 5 clock cycle to get instruction from the I/O memory and write back to register. And the output is 1C. And this is the base address, and then is the data from the input.
So SW is like store word state, or what's your SW state?
Yes, it's the base. I just have the same name of the state. Actually does calculate the base address.
But how does it know whether to go to IO read or like a memory read? You show it always going to IO read. Is it the same state or is it a separate state?
It's the same state because the calculation of the base address is just
Right.
get through, and then
But then how does it know whether to go to IO read or whether to go to a actual
this
store
one's
word
different.
read?
this for the store word, this will go to write back immediate state.
Yeah, the store word, it has to go to one of two places, correct? Whether you're doing an IO access or a memory access, because the address calculation is the same,
Right.
but how does it know which way to branch off?
I think it's from
What if it's a store word instruction?
for the store word is the next one. It's,
Yeah, so that's what I mean. So it can't go to both places without a decision.
no. So I have the same state as like a store state, but in this it.
So that's the question, how does it know which way to go? Because in the previous slide it went one way and in this slide it goes another way. How do you figure out what the next state is from the store word state?
But isn't this state?
No,
is the-
previous state.
This one is not store, this one is input.
So how do you know you're going to one of two states from SW? In this slide you're going to IO read, but in the next slide you're going to like a memory read. So how does the store word state know which way to go?
I'm not sure I understand that. This one is,
See, there you show it going to WBIO. In the previous slide, you show the same next state going to IO read.
oh,
So SW has to make a decision.
so I think this one is wrong then.
Okay, let's go on.
Sorry.
Yeah.
Okay, so this one is just like a store instruction. So for the return from the interrupt, it's the stack pointer starting from 3SC and then read the data from the stack pointer from the bottom to the top. And the last stack pointer is going to be 200 when it return back the return address to the processor. And this is the verification. It has the input, output, and the return from interrupt instruction. And from this module, we expect to see the result would be register 19 to register 21. It consists of the same data content as in the I/O memory module, starting from the address of 0C. So we can look at the stack, we can look at the register, the stack pointer register 29, which is on the top right there, 1D, and the stack pointer content is 3FC. And this is the data memory, the content of the data memory starting from address C0 is the same as 80, it's the same as register 19. The content is the same, so it shows that it executes it the right way. So my current enhancement is pipeline. It's been a little difficult in implementing this. At first, I decided to give up, and then a week later, at the last minute that I have to review my design again, and I was able to generate about 25% of the expected result. Well, it's really small, but I'm really pleased with this result, and I'd like to include the result in this presentation. So the concept behind the pipelining is to execute the instruction every clock cycle. When we look at the multi-cycle instruction, it needs 6 clock to finish the second instruction, which is the store instruction. It finishes at clock 9, the far left back right there. And then for the pipeline implementation, the second instruction is finished at clock 6. So that's the reason the reason pipeline means it increased the throughput, and it's really adhere to the goal of the design of these regular processors. So, but sorry, I have one more thing that I need to mention. But pipelining also raised some issue, which are structural hazard, control hazard, and the data hazard. For the structural hazard, it's an easy fix because in this implementation of the processor, we have 2 memory modules. So the instruction memory, the blue right there, and the data memory, the yellow right here, can be accessed at the same time. Read from the memory module and read from the instruction module. And this is some of the modification I made for the control unit. Instead of using the state machine, I have someone save all the control signals. So all my control signal, which is C and T, and the total bit is 28 bit. If you look at the PCU, the control signal generally, and I have 28 right there, which is the number of the bit of the control signal. And in this blue, red, and yellow, those are the top bit of the control signal that I have for the IDEX stage, execution memory state, and the memory write-back state. The red right here, these are the register that to hold all the control signal. So the first IDEX register, which is the 20, it holds all the 20 bit. The pipeline goes down. The most significant bit of the control signal, which is the yellow part, has been sent out to the execution control in the ALU, and the next one it passed down to the so it go down to 12 bit, and then the 12 bit will chop down to 6 bit, and the last control signal is only 6 bit.
Mm-hmm.
And this is the modification of the hardware design. All the circle, those are the pipeline state. I have ID state, IDEX state, EX memory state, memory write-back state. I add some more 6 more register, and those are the added register are red. All those are in red. And this, and the other one, which is RS forward select, is a select signal input. It's only like 2 bit, and that one is 2 bit too. And this is just the code that I added in the integer data path for the forwarding data in, and then the ALU output, which is the signal come from here to here. And yeah, and this is the last register on the pipeline that hold the data when it come out of the ALU right here. And this is the one the testing module. This is lab 6 that I use for testing module, and it's supposed to write back the result into register 1, and then the first result of the register 7 is that result, and if the code execute all the way to the last, the content of register 7 will be changed. And this is the some of the wavelength as a fetch state right here. You see the first instruction is 3C01123 and the next instruction, and the next clock you see different instruction, and at clock 55 nanoseconds, the last instruction is 3C0CABCD, and see the number 1, 2, 3, 4. That is the content from the last register that I mentioned earlier, and this is the same. So I just put it down. So if we look at the ALU out, we're supposed to see the ALU out is consistently each clock change the number. So 1, 2, 3, 4, 0, 0. The next one is 1, 2, 3, 4, 5, 4, 6, 7, 8, And the next one is 875, and the next one is 8765481. So for each clock cycle, the write back register ready to write back to the AL to the register is consistent output each data each clock. So when I run the test, tested with multi-cycle and the pipeline, the amount of time is different. For the pipeline is 441 nanoseconds. For the multi-cycle is 431 nanoseconds. So the throughput has been improved. So when I look at it, it's really promising, and I like the result. But if you look at it closely, there's a little problem with it. For register 7, the content has been changed as skip. So that means the code executes down here to the break. But I don't have the content to register 8 to 9. See, I don't have anything in 8 to 9. But with the multi-cycle, I have all the content until 15. So that is a problem right there. And then the problem is for the forwarding unit. So for each, if you look at this, so for this instruction, we have the data dependency 7. This instruction depends on the output from this instruction. So it's one instruction depends on the previous instruction, but when one instruction depends on the previous instruction, depends on the second previous instruction. Just like this instruction, my forwarding unit doesn't function properly. This is a good testing tool. It exposes the malfunction of my forwarding unit. It's good. But then it's a little disappointing. But then this is the most result I can generate for this pipeline. So for future enhancement, I plan to make some adjustment to improve the forwarding unit and also the load hazard, branch jump, and the push and pop instruction. I was doing it, but then at the last minute I realized that it was wrong because I made a wrong selection on register 8 right there. So it was a little confusing, but by the time I find out, I already submit my project, but it's wrong data right there. Thank you for listening.
Thank you. That was excellent. Very good.